In this lecture, I want to discuss the biofuel energy processes and application. The biofuel energy processes are classified by the thermochemical process, biochemical process, and the agrochemical process. In this lecture, I only discuss the direct combustion process of the thermochemical processes. The biofuel energy processes are mainly classified by thermochemical process, biochemical process, and the agrochemical process. The thermochemical process includes the direct combustion process, pyrolysis process, and the other thermochemical process. The biochemical processes are consist of the aerobic digestion process, anaerobic digestion process, alcoholic fermentation process, and the biophotolysis process. Similarly, the agrochemical process are also classified by the fuel extraction process and the biodiesel and esterification process. In this lecture, I elaborately discuss on the direct combustion process. The total biofuel production process are described in this flowchart. In this flowchart, the biomass production is divided by thermochemical process, biochemical process, and the agrochemical process. The thermochemical process is again divided by the direct combustion process. The direct combustion for the immediate heat. This is the major use of firewood and logs in both the developing and developed world. Dry homogeneous input is much preferred. Best results have the dry wood burning in a stove, oven or boiler with control of the incoming air so that there is full but not excessive combustion is there. Air entry is needed around the fuel for initial combustion and into the hot exhaust for the secondary combustion. Some biomass such as sawmill, waste or purposely produced sawdust is densified by only compression into the pellets. Pellets is nothing but a size of 15 mm cross 5 mm, or the briquettes, that is the dimension is 100 mm cross 40 mm. This process makes the biomass easier and cheaper to transport and delivered to stores, easier to feed directly from the store into the combustion chambers with the auger screws, and it is easier to control the combustion with the injected air. Consequently, there is now substantial regional and international trade in the wood pellets. The municipal solid waste, that is MSW, and the dried sewage can be processed by densification to produce the solid combustion fuels. Second is the pyrolysis, including the gasification. Pyrolysis, biomass is heated either in the absence of air or by the partial combustion of some of the biomass in a restricted air or oxygen supply. The products are extremely varied, consisting of gases, vapors, liquids and oils, and the solid car and ash. The output depends on the temperature, types of input material and treatment process. In some processes, the presence of water is necessary, and therefore the material need not to be dry. So if the output of the combustible gas is the main product, the process is called the gasification. This is the gasification. So traditional charcoal making and the modern torrefaction at moderate temperatures of the 200 degree to 300 degree centigrade produce the solid cur as desired the product. And the other thermochemical process that is called the further processes. This includes a wide range of pre-treatment and process operations are possible in this step. These normally involve the sophisticated chemical control and industrial scale of manufacture. Methanol production is such a process. Example for the liquid fuel. Of particular importance are processes that break down the cellulose and starches into the sugars for subsequent fermentation. Then come to the biochemical process. Biochemical process, there is the aerobic digestions are there. In the presence of air, the microbial aerobic metabolism of biomass generates the heat with the emission of carbon dioxide but not methane. This process is of the great significance for the biological carbon cycle. Example of the decay of forest litter and for the sewage processing, but it is not used significantly for the commercial bioenergy. Then come to the anaerobic digestion. This is very much important. In the absence of free oxygen, certain microorganisms can obtain their own energy supply by reacting with the carbon compounds of the medium. Reduction level to produce both the carbon dioxide and fully reduced carbon as methane. The process may also be called the fermentation, but is usually called the digestion because of the similar process that occurs in the digestive tracts of the ruminant animals. The evolved mixture of carbon dioxide and methane and trace gases is called the biogas as a general term, but may be called the sewage gas or the landfill gas as appropriate. Then come to the alcoholic fermentation. Ethanol is the volatile liquid fuel that may be used in the place of refined petrol, which is called the gasoline. It is manufactured by the action of microorganisms and is therefore a fermentation process. Conventional ethanol has sugars as feedstock, which may have been produced from starch by other microorganisms in a preliminary process of malting. Then come to the biophotolysis. This is the biophotolysis. The photolysis is the splitting of water into the hydrogen and oxygen by the action of light. Recombination occurs when the hydrogen is burned or exploded as a fuel in air. Certain biological organisms produce or can be made to be produce hydrogen in the biophotolysis. Similar results can be obtained chemically without living organisms under the laboratory conditions. Yields are small, so the R&D activities are continued for the commercial exploration. Then come to the agrochemical process. This is the agrochemical process, just called the fuel extraction. Occasionally, the liquid or solid fuels may be obtained directly from the living or freshly cut plants. The materials are called the exudates and are obtained by cutting into the stems or trunks of living plants or by crushing the freshly harvested material. A well-known similar process is the production of natural rubber latex. Related plants to the rubber plant Hieria, such as the species of Euphorbia, produce the hydrocarbons of less molecular weight than the rubber, which may be used as the petroleum substitute and the turpentine. Some varieties of algae likewise produce hydrocarbons directly at high yield per unit area. Then the biodiesel and the esterification. Concentrated vegetable oils from the plants may be used directly as fuel in the diesel engines. Indeed, the Rudolf Diesel designed his original 1892 engine to run on a variety of fuels, including natural plant oils. However, difficulties arise with direct use of plant oil due to the high viscosity and the combustion deposits as compared with the standard diesel fuel engine, mineral oil, especially at low ambient temperature. Both difficulties are overcome by converting the vegetable oil to the corresponding ester, which is arguably a fuel better suited to diesel engine than the conventional diesel oil. Then come to the direct combustion for heat. Biomass is burned to provide the heat for cooking, the comfort heat, that is called space heat, crop drying, factory processes, and raising steam for electricity production and transport. Traditional use of biomass combustion includes the cooking with firewood, with the latter perhaps supplying about 15% of the global energy use, and the commercial and industrial use for the heat and power. Efficiency and minimum pollution are aided by using the dry fuel and controlled high temperature combustion. The direct combustion of heat, like the domestic cooking. A significant proportion of the world's population depends on the fuel wood or the other biomass for cooking, heating, and other domestic uses. An average consumption of 150 watt continuous solely for cooking may seem surprisingly large. The average daily consumption of the fuel is about 0.5 to 1 kg of dry biomass per person, such that the 10 to 20 megajoules per day, that is called 150 watt, multiplied by say 2 into 10 to the power 9 people, this represents the energy usage at the very substantial rate of 300 gigawatt. Most domestic fuel wood use, but certainly not all, is in developing countries, with the majority not included in the commercial energy statistics. Here we assume the fuel has dried thoroughly since this is an essential first step for the biomass combustion. Using the wet or the damp fuel should be avoided. Such a large consumption arises from the widespread use of the inefficient cooking methods, the most common of which is an open fire. Such methods may have a thermal efficiency of heating the food of only about 5%, although the three-stone fireplace allows wood to be pushed in for controlled combustion and the improved efficiency. The lost energy includes the incomplete combustion of the wood, wind dispersing heat away from the fire, and by radiation and the convective losses from the mismatch of fire and the pot size. Considerably energy is also wasted in evaporation from uncovered pots and from the wet fuel. Smoke from a fire is evidence of the incomplete combustion, and there may be little control over the rate at which the wood is burned. Moreover, the smoke is a health hazard unless there is an efficient extraction chimney. However, a reason for allowing the internal smoke may be to deter vermin and pests from the roof and to cure the dried food. Efficiently burned dry wood, in which the initially produced unburned gases and tars burn in a secondary reaction, emits only carbon dioxide and H2O with the fully combusted ash. Cooking efficiency and the facilities can be improved by using the dry fuel, introducing alternative foods and cooking methods, just like steam cookers, decreasing heat losses using the enclosed burners or the stoves, and well-fitting pots with lids, facilitating the secondary combustion of the unburned flue gases, introducing stove controls that are robust and easy to use. Explanation, training, and the management should be required. With these improvements, the best cooking stoves using the fuel wood and the natural air circulation can place more than 20% of the combustion energy into the cooking pots. Designs using forced and actively controlled ventilation, say with an electric fan, can be more than 80% efficient, but cooking may be very slow. There are many scientifically based programs to improve the cooking stoves, yet full market acceptability is not always reached, especially if the cultural and gender factors are not considered adequately. By far the largest such program has been in China, with over 170 million new stoves in use, mostly in rural areas. In Rwanda, more than half of all households now have such stoves, with the proportion increasing. The World Bank in 2010 has reviewed the lessons learned from many such programs. Successful programs offer a wide range of efficient stove designs tailored to user requirements and sold commercially. The stoves have proven efficiency, the ability to reduce the indoor air pollution, and the good durability, and are very safe. The combustion of firewood is a complex and varying process. Much depends on the type of wood and its moisture content. Initial combustion releases carbon monoxide, which itself should burn in surplus air. At temperatures greater than 370 degrees centigrade, the calcium oxalate in the wood breaks down with the release of some oxygen, so improving combustion and reducing particulate and the combustible emissions. Good design ensures that the high temperature combustion is restricted to a white hot small volume by directed, perhaps forced, air entry, and that the pyrolytic gases are themselves burnt in a secondary combustion region where the further air enters. If the space heating is needed, then the seemingly wasted heat from the cooking becomes useful. A parallel method for reducing domestic fuel wood demand is to encourage alternative renewable energy supplies, such as the biogas, just like a methane with carbon dioxide, fuel from the crops waste, and the small-scale hydropower. The need for such improvements is overwhelming when the forests are dwindling and deserts increase. The figure shows two types of wood-burning stoves. Designed to make the better use of wood as a cooking fuel. Both designs are cheap enough to allow the widespread use in the developing countries. More expensive stoves, often called ranges, for both cooking and the water heating are luxury items in many kitchens of the Northern European and the North American homes, where some designs allow the wood burning. In the stove shown in the figure A, the fire is completely enclosed in the firebox on the left. The iron, that is the dark color, black color here, the iron door is removed only when the fuel is inserted. This is the iron door. Air enters through a hole of the adjustable size beneath the door, fully shut in the photo. Thus, the rate of combustion can be closely controlled to match the type of cooking being done. Hot gases from the fire are led through a narrow channel underneath the cooking pots, which are sized to fit closely in the hole on the top. At this stage, the air can enter through further channels for the secondary combustion. The fully burned gases and the vapors pass to the outside environment through the chimney at the far end of the stove. This prevents the pollution in the cooking area and encourages the airflow. In the figure B, the stove is simpler and cheaper, but has the less control and less flexibility. Nevertheless, its small mass means that it is transportable and little heat is used in heating the stove as distinct from the pot, which is an advantage for the quick cooking. Air reaches the fuel from the below through a grate. Since the fire is contained and the heat is channeled towards the pot, the efficiency is very high. The grate is made by the ceramic. This stove is well suited for use with the charcoal as a fuel, since the charcoal burns cleanly without smoke. For comfort or the space heating in the buildings, as with the cooking stoves, it is important for the stove or the central heating boiler to have a controlled fire with the good secondary combustion. Efficiency is improved if air for the combustion is introduced directly to the combustion chamber from outside the building, which decreases the internal draughts and the heat loss. Sophisticated and efficient wood burners for heating are in widespread use, especially in some wood-rich industrialized countries, just like Norway, Canada, and New Zealand. If the useful heat is the heat delivered beneficially, then enclosed stoves and boilers with the controlled primary and secondary combustion can be 80 to 90% efficient. Some countries, just like in Northern Europe, encourage the markets in the fuel wood chips and the pellets. Although the main market for these products may be for co-firing with the coal in the power stations, they are used for space heat and hot water in the individual buildings. For the latter, there are specially designed sophisticated stoves with the automatic input of the fuel, which are easy to use, have excellent fuel efficiency, and are the clean with the minimum pollution. Now the crop drying, direct combustion for heat using the crop drying. The drying of the crops, example the fruits, copra, cocoa, coffee and tea for the storage and the subsequent sale is commonly accomplished by the burning wood and the crop residues or by using the waste heat from the electricity generation. Here this is the figure shown as the crop drying plant. The material to be dried may be placed directly in the flue exhaust gases, but there is a danger of fire and the contamination of the food products. More commonly, the air is heated in a gas or air heat exchanger before passing through the crop. The combustion of the harvest residues for the crop drying is a rational use of the biofuel since the fuel is close to where it is needed. The combustion in an efficient furnace yields a stream of hot, clean exhaust gas including the carbon dioxide, the vapor and the excess air at about 1000 degrees centigrade, which can be diluted with the cold air to the required temperature. If the amount of biomass residue exceeds that required for the crop drying, the excess may be used for the other purposes such as the producing industrial stream. This is an important mechanism, crop drying mechanism shown in the figure. Now the processed heat and the electricity. Steam processed heat is commonly obtained for the factories by burning wood or other biomass residues in boilers, perhaps operating with the fluidized bed. It is physically sensible to use the steam first to generate the electricity before the heat degrades to a lower useful temperature. The fluidized bed combustor as shown in the figure. This is the combustor. The enlarged view of the combustor is shown in the figure here. The burned biomass fuel in a hot bed of the granular material such as sand. Injection of air into the bed creates the turbulence resembling a boiling liquid. The turbulence distributes and suspends the fuel. The design of a fluidized bed reactor increases heat transfer and allows for operating temperatures below the 950 degrees centigrade, reducing the nitrogen oxide emissions. Fluidized bed combustor can handle the high ash fuels, agricultural residues, and the sewage sludge. The efficiency of the electricity generation from the biomass may be only about 20 to 25% due to the low temperature combustion. So the 75 to 80% of the energy remains as process heat and a useful final temperature is maintained. Frequently, the optimum operation of such processes treats electricity as a byproduct of the process heat generation, with excess electricity being sold to the local electricity supply agency, as in modern sugarcane mills as shown in the figure. The flow diagram shown in the figure indicates how a single crop, just like a sugar cane, may be processed for both energy supplies and a wide range of products with no other inputs than just the locally grown cane. The cane stems about 3 meter long by 5 centimeter diameter are harvested and then transported in bulk, either by lorries or on a light railway led over the surrounding fields to a certain mill. Here the steam power rollers crush the cane to extract the juice as the main initial product. The juices pass principally for the sugar extraction, with the residues like the molasses used directly for the cattle feed, fermented on site to ethanol for sparkingation vehicle biofuel, and it is used in pharmaceutical and other specialist chemicals. The cane's fibrous residue from the rollers, that is called the bagages, is burnt in boilers to raise the steam to generate the electricity and supplying the heat for the mill processes, notably boiling the juice to extract the solid sugar. The surplus bagages is pressed with the binder to make the fiber board for building construction. The fiber products. The boiler ash becomes a phosphate-rich fertilizer. With the modern efficient machinery, there should be excess electricity generation for the sale to the utility distribution grid. A relatively easy way to use the energy crops and the biomass residues is co-firing in coal burning power station. The combustion method is adapted for the known mixture of coal and the biomass. Having a uniform fuel gives the most reliable operation, so densified products such as wood pellets are favored. Torrefaction, that is called the controlled low temperature pyrolysis to produce the care of the mixed biomass before combustion, improves the final combustion in the boilers. The co-firing of the biomass may be implemented using the different types and percentages of the biomass in a range of combustion and gasification technologies. Most forms of the biomass are suitable for co-firing. This includes the dedicated energy crops, urban wood waste, and the agricultural residues such as the rice straw and the rice husk. The fuel preparation requirements issues associated with the combustion such as the corrosion and the fouling of the boiler tubes and the characteristics of the residual ash dictate the co-firing configuration appropriate for a particular plant and the biomass resource. These configurations may be categorized into the direct co-firing, indirect co-firing, and the parallel co-firing. The direct co-firing, this is the most common form of the biomass co-firing, involving the direct co-firing of the biomass fuel and the primary fuel, generally coal, in the combustion chamber of the boiler. The cheapest and the simplest form of the direct co-firing for the pulverized coal power plant is through mixing prepared biomass and the coal in the coal ear or on the coal conveyor belt before the combined fuel is fed into the power station boiler. Then come to the indirect co-firing. If the biomass fuel has different attributes to the normal fossil fuel, then it may be prudent to partially segregate the biomass fuel rather than the risk damage to the complete station. For the indirect co-firing, the ash of the biomass resource and the main fuel are kept separate from one another as the thermal conversion is partially carried out in separate processing plants. As indirect co-firing requires a separate biomass energy conversion plant, it has a relatively high investment cost compared with the direct co-firing. Then come to the parallel co-firing. For the parallel firing, totally separate combustion plants and the boilers are used for the biomass resource and the coal-fired power plants. The steam produced is fed into the main power plant where it is upgraded to higher temperatures and pressures to give the resulting higher energy conversion efficiencies. This allows the use of problematic fuels with high alkaline and the chlorine contents and the separation of the ashes. In recent years, a substantial international trade in the wood pellets has arisen, notably from the Russia and the Canada into the Western Europe. Such substitution of the coal is a realistic policy for biomass to reduce the greenhouse gas emissions in the short term, despite the intrinsic efficiency of all such power stations without combined the heat and the power being only about the 35%. Now the predominant technology in the world today for electricity generation from the biomass at scales above 1 megawatt is the steam Rankine cycle as shown in the figure. This consists of direct combustion of the biomass in a boiler to raise the steam, which is then expanded through the turbine. The steam Rankine technology is a mature technology introduced into the commercial use about 100 years ago. The typical capacity of the existing biomass power plants ranges from 1 to 50 megawatt, with an average around of 20 megawatt. Energy conversion efficiencies are relatively low, 15 to 25%, due to their small size, although the technologies and the process to increase these efficiencies are being developed. Such combined 15 heat and the power, that is called the CHP, combined heat power, or the cogeneration systems provide greater levels of energy services per unit of the biomass consumed than systems that only generate the power and can reach the overall efficiencies of greater than 80%. The difference between the cogeneration and the direct fire gas turbine technology and the co-firing is that the cogeneration using a boiler to produce the heat and the electricity, where the conversion efficiency is 85%. The electricity production from the steam driven turbine generators is 70 to 25% conversion efficiency. In the direct fire gas turbine technology, the fuel pre-treatment reduces the biomass to a particle size less than 2 mm and a moisture content of the less than is 25%. Fuel is burnt in the compressed air, then go to the turbine, then it is produced the electricity. But in co-firing, the biomass is used as the secondary fuel, could help to reduce the sulfur dioxide and the nitrogen oxide emissions, decreases the net carbon dioxide emissions from the power plant. The CHP, that is called cogeneration, is described in the figure. Steam cycle plants are often located at industrial sites where the waste heat from the steam turbine is recovered and used for meeting the industrial process heat needs. The cost of the steam Rankine systems vary widely depending on the type of the turbine, type of the boiler, the pressure and the temperature of the steam and the other factors. An important characteristics of this type of steam turbines and the boilers is that their capital costs are scale sensitive. This, together with the fact that the biomass steam Rankine systems are constrained to relatively small scales due to biomass fuel transport cost limitations, typically leads to biomass steam Rankine systems that are designed to reduce the capital cost at the expense of efficiency. For example, the biomass fire systems are typically designed with much more modest steam pressure and temperature than is technologically feasible, enabling lower grade steels to be used in the boiler tube. This lowers both the cost and the efficiency also. Even with such measures to reduce the cost, however, the capital cost for small scale systems are still substantial and lead to relatively high electricity generating cost compared to the conventional fossil energy power plants. Consequently, the existing biomass power plants rely on low, zero or negative cost biomass, such as primarily residues of the agro and the forest product industry operations. Since there are untapped supplies of the low-cost biomass feedstocks available in many regions of the world, the economics of the steam Rankine systems are probably reasonable. An alternative to the above described direct fire biomass combustion technologies and consider the nearest term low-cost option is biomass co-combustion with the fossil fuels in the existing boilers. Successful demonstrations using the biomass as a supplementary energy source in large high-efficiency boilers have been carried out, showing that the effective biomass fuel substitution can be made in the range of 10 to 15% of the total energy input with the minimal plant modifications and the no impact on the plant efficiency and operation. This strategy is economical when the biomass fuels are lower cost than the fossil fuels used. For the fossil fuel plant capacities greater than the 100 megawatt per year, this can mean a substantial amount of biomass and related carbon savings and emissions reductions, particularly for the coal substitution. These are the references from where I made this lecture. You should go through this reference. Thank you.